Learning objectives. In this chapter, the user would learn the following in detail: protection, goals of protection, domain of protection, access matrix, implementation of access matrix, revocation of access rights, security, the security problem, authentication, one-time passwords, program threats, system threats, threat monitoring, encryption, computer security classifications, common criteria, VPN protocol security, access checks, ACL, DACLs, auditing and policy management, user account controls, UAC. Access checks, ACL, DACLs. Access checks is the traditional center of gravity of computer security. Access checks are also said as access control. It is where security engineering meets computer science. Its function is to control which principals, persons, processes, machines and so on have access to which resources in the system, which files they can read, which programs they can execute, how they share data with other principals and so on. Access control works at a number of levels as shown in figure and described in the following. The access control mechanisms which the user sees at the application level may express a very rich and complex security policy. A modern online business could assign staff to one of dozens of different roles, each of which could initiate some subset of several hundred possible transactions in the system. Some of these, such as credit card transactions with customers, might require online authorization from a third party, while others, such as refunds, might require dual control. The applications may be written on top of middleware such as database management system or bookkeeping package which enforces a number of protection properties. For example, bookkeeping software may ensure that a transaction that debits one ledger for a certain amount must credit another ledger for the same amount. The middleware will use facilities provided by the underlying operation system. As this constructs resources such as files and communications ports from lower-level components, it acquires the responsibility for providing ways to control access to them. Finally, the operating system access controls will usually rely on hardware features provided by the processor or by associated memory management hardware. These control which memory addresses a given process can access. As we work up from the hardware through the operating system and middleware to the application layer, the controls become progressively more complex and less reliable. Most actual computer frauds accidentally discovering features of the application code that they can exploit in an opportunistic way or just abusing features of the application that they were entrusted not to. But in this chapter we will focus on the fundamentals, access control at the hardware and operating system level. As with the other building blocks discussed so far, access control makes sense only in the context of a protection goal, typically expressed as a security policy. This puts us at a slight disadvantage when discussing PCs running single-user operating systems such as DOS and Windows 95/98, which have no overt security policy. Any process can modify any data. People do have implicit protection goals, though you don't expect a shrink-wrap program to trash your hard disk. So an explicit security policy is a good idea, especially when products support some features that appear to provide protection such as login IDs. Operating system access controls. The access controls provided with an operating system typically authenticate principals using some mechanism such as passwords or Kerberos, then mediate the access to files, communication ports, and other system resources. Their effect can often be modeled by a matrix of access permissions with columns for files and rows for users. We'll write R for permission to read, W for permission to write, X for permission to execute a program, and minus for no access at all as shown in figure below. In this simplified example, Sam is the system administrator and has universal access except to the audit trail, which even he should only be able to read. Alice, the manager, needs to execute the operating system and application, but only through the approved interfaces. She mustn't have the ability to tamper with them. She also needs to read and write the data. Bob, the auditor, can read everything. This is often enough, but in the specific case of a bookkeeping system, it's not quite what we need. We want to ensure that transactions are well formed, that each debit is matched by a credit somewhere, so we would not want Alice to have uninhibited write access to the account file. We would also prefer that Sam didn't have this access, so that all write access to the accounting data file was via the accounting program. The access permissions might now look like those shown in figure. Another way of expressing a policy of this type would be with access triples of user, program, file. In the general case, our concern isn't with a program as much as the protection domain, which is a set of processes or threads that share access to the same resources, though at any given time they might have different files open or different scheduling priorities. Access control matrices, whether in 2 or 3 dimensions, can be used to implement protection mechanisms as well as just model them, but they do not scale well. For instance, a bank with 50,000 staff and 300 applications would have an access control matrix of 15 million entries. This is inconveniently large. It might not only impose a performance problem but also be vulnerable to administrators' mistakes. We will usually need a more compact way of storing and managing this information. The 2 main ways of doing this are to use groups or roles to manage the privileges of large sets of users simultaneously, or to store the access control matrix either by columns, access control lists, or rows, capabilities sometimes known as tickets or certificates. Access control lists. Another way of simplifying access rights management is to store the access control matrix a column at a time along with the resource to which the column refers. This is called an access control list or ACL. In the first of the examples, the ACL for file 3, the account file might look as shown in figure below. ACLs have a number of advantages and disadvantages as a means of managing security state. These can be divided into general properties of ACLs and specific properties of particular implementations. ACLs are widely used in environments where users manage their own file security, such as the Unix systems common in universities and science labs. Where access control policy is set centrally, they are suited to environments where protection is data-oriented. They are less suited where the user population is large and constantly changing, or where users want to be able to delegate their authority to run a particular program to another user for some set period of time. ACLs are simple to implement but are not efficient as a means of doing security checking at runtime, as the typical operating system knows which user is running a particular program rather than which files it has been authorized to access since it was invoked. The operating system must either check the ACL at each file access or keep track of the active access rights in some other way. Finally, distributing the access rules into ACLs can make it tedious to find all the files to which a user has access. Revoking the access of an employee who has just been fired, for example, will usually have to be done by cancelling their password or other authentication mechanism. An access control list ACL is a list of access control entries ACE. Each ACE in an ACL identifies a trustee and specifies the access rights allowed, denied, or audited for that trustee. The security descriptor for a securable object can contain 2 types of ACLs, a DACL and a SACL. A discretionary access control list DACL identifies the trustees that are allowed or denied access to a securable object. When a process tries to access a securable object, the system checks the ACEs in the object's DACL to determine whether to grant access to it. If the object does not have a DACL, the system grants full access to everyone. If the object's DACL has no ACEs, the system denies all attempts to access the object because the DACL does not allow any access rights. The system checks the ACEs in sequence until it finds one or more ACEs that allow all the requested access rights or until any of the requested access rights are denied. For more information, see how DACLs control access to an object. For information about how to properly create a DACL, see Creating a DACL. A System Access Control List (SACL) enables administrators to log attempts to access a secured object. Each ACE specifies the types of access attempts by a specified trustee that cause the system to generate a record in the security event log. An ACE in a SACL can generate audit records when an access attempt fails, when it succeeds, or both. For more information about SACLs, see Audit Generation and SACL Access Right. Do not try to work directly with the contents of an ACL. To ensure that ACLs are semantically correct, use the appropriate functions to create and manipulate ACLs. For more information, see Getting Information from an ACL and Creating or Modifying an ACL. ACLs also provide access control to Microsoft Active Directory Service objects. Active Directory Service Interfaces (ADSI) include routines to create and modify the contents of these ACLs. For more information, see Controlling Access to Active Directory Objects. Access Matrix. A general model of protection can be viewed abstractly as a matrix called an access matrix. The rows of the access matrix represent domains and the columns represent objects. Each entry in the matrix consists of a set of access rights. Because the column defines objects explicitly, we can omit the object name from the access right. The entry access ij defines a set of operations that a process executing in domain DI can invoke on object OJ. To illustrate these concepts, we consider the access matrix shown in figure below. There are 4 domains and 4 objects, 3 files, F1, F2, F3, and 1 laser printer. A process executing in domain D1 can read files F1 and F3. A process executing in domain D4 has the same privileges as one executing in domain D1, but in addition it can also write onto files F1 and F3. The laser printer can be accessed only by a process executing in domain D2. The access matrix scheme provides us with the mechanism for specifying a variety of policies. The mechanism consists of implementing the access matrix and ensuring that the semantic properties we have outlined hold. More specifically, we must ensure that a process executing in domain DI can access only those objects specified in row I and then only as allowed by the access matrix entries. The access matrix can implement policy decisions concerning protection. The policy decisions involved which rights should include in the ijth entry. We must also decide the domain in which each process executes. This last policy is usually decided by the operating system. The users normally decide the contents of the access matrix entries. When a user creates a new object OJ, the column OJ is added to the access matrix with the appropriate initialization entries as dictated by the creator. The user may decide to enter some rights in some entries in column J and other rights in other entries as needed. The access matrix provides an appropriate mechanism for defining and implementing strict control for both static and dynamic association between processes and domains. When we switch a process from one domain to another, we are executing an operation switch on an object, the domain. We can control domain switching by including domains among the objects of the access matrix. Similarly, when we change the content of the access matrix, we are performing an operation on an object, the access matrix. Again, we can control these changes by including the access matrix itself as an object. Actually, since each entry in the access matrix can be modified individually, we must consider each entry in the access matrix as an object to be protected. Now we need to consider only the operations possible on these new objects, domains, and the access matrix, and decide how we want processes to be able to execute these operations. Processes should be able to switch from one domain to another. Switching from domain DI to domain DJ is allowed if and only if the access right switch *access IJ. Thus, in figure below, figure shows access matrix of figure with domains as objects. Below, a process executing in domain D2 can switch to domain D3 or to domain D4. A progress in domain D4 can switch to D1, and one in domain D1 can switch to D2. Allowing controlled change in the contents of the access matrix entries requires three additional operations: copy, owner, and control. We examine these operations next. Access matrix. The ability to copy an access right from one domain or row of the access matrix to another is denoted by an asterisk appended to the access right. The copy right allows the access right to be copied only within the column, that is, for the object for which the right is defined. For example, in figure below A, a process executing in domain D2 can copy the read operation into any entry associated with file F2. Hence, the access matrix of figure A can be modified to the access matrix shown in figure B. This scheme has two additional variants. A write is copied from access IJ to access KJ. It is then removed from access IJ. This action is a transfer of a write rather than a copy. Propagation of the copy write may be limited. That is, when the write R asterisk is copied from access IJ to access KJ, only the write R, not R asterisk, is created. A process executing in domain DK cannot further copy the write R. A system may select only one of these three copyrights, or it may provide all three by identifying them as separate writes: copy, transfer, and limited copy. We also need a mechanism to allow addition of new writes and removal of some writes. The owner right controls these operations. If access IJ includes the owner right, then a process executing in domain DI can add and remove, is the owner of F1, and thus can add and delete any valid write in column F1. Similarly, domain D2 is the owner of F2 and F3, and thus can add and remove any valid write within these two columns. Thus, the access matrix of figure below A can be modified to the access matrix shown in figure below B. The copy and owner rights allow a process to change the entries in a column. A mechanism is also needed to change the entries in a row. The control right is applicable only to domain objects. If access IJ includes the control right, then a process executing in domain DI can remove any access right from row J. For example, suppose that in figure below we include the control right in access D2, D4. Then, a process executing in domain D2 could modify domain D4 as shown in figure below. The copy and owner rights provide us with a mechanism to limit the propagation of access rights. However, they do not give us the appropriate tools for preventing the propagation or disclosure of information. The problem of guaranteeing that no information initially held in an object can migrate outside of its execution environment is called the confinement problem. This problem is in general unsolvable. These operations on the domains and the access matrix are not in themselves important, but they illustrate the ability of the access matrix model to allow us to implement and control dynamic protection requirements. New objects and new domains can be created dynamically and included in the access matrix model. However, we have shown only that the basic mechanism exists. System designers and users must make the policy decisions concerning which domains are to have access to which objects in which ways. Implementation of the access matrix. How can the access matrix be implemented effectively? In general, the matrix will be sparse, that is, most of the entries will be empty. Although data structure techniques are available for representing sparse matrices, they are not particularly useful for this application because of the way in which the protection facility is used. Here we first describe several methods of implementing the access matrix and then compare the methods. Global table. The simplest implementation of the access matrix is a global table consisting of a set of ordered triples, domain, object, rights set. Whenever an operation M is executed on an object OJ within domain DI, the global table is searched for a triple DI OJ RK with M asterisk RK. If this triple is found, the operation is allowed to continue. Otherwise, an exception or error condition is raised. This implementation suffers from several drawbacks. The table is usually large and thus cannot be kept in main memory, so additional input-output is needed. Virtual memory techniques are often used for managing this table. In addition, it is difficult to take advantage of special groupings of objects or domains. For example, if everyone can read a particular object, this object must have a separate entry in every domain. Access lists for objects. Each column in the access matrix can be implemented as an access list for one object. Obviously, the empty entries can be discarded. The resulting list for each object consists of ordered pairs, domain, right set, which define all domains with a non-empty set of access rights for that object. This approach can be extended easily to define a list plus a default set of access rights. When an operation M on an object OJ is attempted in domain DI, we search the access list for object OJ looking for an entry DI RK with M asterisk RK. If the entry is found, we allow the operation. If it is not, we check the default set. If M is in the default set, we allow the access. Otherwise, access is identified and an exception condition occurs. For efficiency, we may check the default set first and then search the access list. Capability lists for domains. A capability list for a domain is a list of objects together with the operations allowed on those objects. An object is often represented by its physical name or address called a capability. To execute operation M on object OJ, the process executes the operation M, specifying the capability or pointer for object OJ as a parameter. Simple possession of the capability means that access is allowed. The capability list is associated with a domain, but it is never directly accessible to a process executing in that domain. Rather, the capability list is itself a protected object maintained by the operating system and accessed by the user only indirectly. Capability-based protection relies on the fact that the capabilities are never allowed to migrate into any address space directly accessible by a user process where they could be modified. If all capabilities are secure, the object they protect is also secure against unauthorized access. Capabilities were originally proposed as a kind of secure pointer to meet the need for resource protection that was foreseen as multi-programmed computer systems came of age. The idea of an inherently protected pointer provides a foundation for protection that can be extended up to the application level. To provide inherent protection, we must distinguish capabilities from other kinds of objects, and they must be interpreted by an abstract machine on which higher-level programs run. Capabilities are usually distinguished from other data in one of two ways. Each object has a tag to denote whether it is a capability or accessible data. The tags themselves must not be directly accessible by an application program. Hardware or firmware support may be used to enforce this restriction. Although only one bit is necessary to distinguish between capabilities and other objects, more bits are often used. This extension allows all objects to be tagged with their types by the hardware. Thus, the hardware can distinguish integers, floating point numbers, pointers, booleans, characters, instructions, capabilities, and uninitialized values by their tags. Alternatively, the address space associated with a program can be split into two parts. One part is accessible to the program and contains the program's normal data and instructions. The other part, containing the capability list, is accessible only by the operating system. A segmented memory space is useful to support this approach. A lock key mechanism. The lock key scheme is a compromise between access lists and capability lists. Each object has a list of unique bit patterns called locks. Similarly, each domain has a list of unique bit patterns called keys. A process executing in a domain can access an object only if that domain has a key that matches one of the locks of the object. As with capability lists, the list of keys for a domain must be managed by the operating system on behalf of the domain. Users are not allowed to examine or modify the list of keys or locks directly. Comparison. As you might expect, choosing a technique for implementing an access matrix involves various trade-offs. Using a global table is simple. However, the table can be quite large and often cannot take advantage of special groupings of objects or domains. Access lists correspond directly to the needs of users. When a user creates an object, he can specify which domains can access the object as well as what operations are allowed. However, because access right information for a particular domain is not localized, determining the set of access for each domain is difficult. In addition, every access to the object must be checked, requiring a search of the access list. In a large system with long access lists, this search can be time-consuming. Capability lists do not correspond directly to the needs of users, but they are useful for localizing information for a given process. The process attempting access must present a capability for that access. Then, the protection system needs only to verify that the capability is valid. Revocation of capabilities, however, may be inefficient. The lock key mechanism, as mentioned, is a compromise between access lists and capability lists. The mechanism can be both effective and flexible, depending on the length of the keys. The keys can be passed freely from domain to domain. In addition, access privileges can be effectively revoked by the simple technique of changing some of the locks associated with the object. Most systems use a combination of access lists and capabilities. When a process first tries to access an object, the access list is searched. If access is denied, an exception condition occurs. Otherwise, a capability is created and attached to the process. Additional references use the capability to demonstrate swiftly that access is allowed. After the last access, the capability is destroyed. This strategy is used in the Multics system and in the ACL system. As an example of how such a strategy works, consider a file system in which each file has an associated access list. When a process opens a file, the directory structure is searched to find the file, access permission is checked, and buffers are allocated. All this information is recorded in a new entry in a file table associated with the process. The operation returns an index into this table for the newly opened file. All operations on the file are made by specification of the index into the file table. The entry in the file table then points to the file and its buffers. When the file is closed, the file table entry is deleted. Since the file table is maintained by the operating system, the user cannot accidentally corrupt it. Thus, the user can access only those files that have been opened. Since access is checked when the file is opened, protection is ensured. This strategy is used in the Unix system. The right to access must still be checked on each access, and the file table entry has a capability only for the allowed operations. If a file is opened for reading, then a capability for read access is placed in the file table entry. If an attempt is made to write onto the file, the system identifies this protection violation by comparing the requested operation with the capability in the file table entry. Access control. A good example of access control is Solaris 10. Solaris 10 advances the protection available in the operating system by explicitly adding the principle of least privilege via Role-Based Access Control (RBAC). This facility revolves around privileges. A privilege is the right to execute a system call or to use an option within that system call, such as operating a file with write access. Privileges can be assigned to processes, limiting them to exactly the access they need to perform their work. Privileges and programs can also be assigned to roles. Users are assigned roles or can take roles based on passwords to the roles. In this way, a user can take a role that enables a privilege, allowing the user to run a program to accomplish a specific task as depicted in figure below. Role-based access control in Solaris 10. This implementation of privileges decreases the security risk associated with superusers and set UID programs. Auditing. Auditing is a useful security technique. Auditing, accounting, and logging can decrease system performance, but they are useful in several areas including security. Logging can be general or specific. All system call executions can be logged for analysis of program behavior or misbehavior. More typically, suspicious events are logged. Windows 7 has built-in auditing that allows many common security threats to be monitored. Examples include failure auditing for login and log-off events to detect random password break-ins, success auditing for login and log-off events to detect login activity at strange hours, success and failure write access auditing for executable files to track a virus outbreak, and success and failure auditing for file access to detect access to sensitive files. It can deliver significant benefits to the audit process in terms of timelines, efficiency, professionalism, and increased productivity. Audit automation is generally considered under two main headings: as an audit tool, as an administration tool. Audit tools. Audit automation in this context involves the use of computer-assisted audit techniques CAATs as an integral part of an audit review to increase its overall efficiency and effectiveness. CATs are generally categorized into those which review data and those which review controls. Those CATs which review data generally involve the extraction, examination, and manipulation of data by programs. Such techniques can enable the auditor to gain an assurance as to the accuracy and integrity of the data being reviewed and, by implication, the strength or weakness of control. Those CATs which review controls look at the system rather than data and provide the auditor with an assurance as to whether or not controls exist and are functioning effectively. By implication, this will cause the auditor to question the accuracy and integrity of that data. Traditional textbooks on computer audit usually refer to a large range of CATs. Although some of these are used to varying degrees by some organizations, in practice, interrogation software is the most widely used CAT. Interrogation software. Interrogation software involves the production of a computer program to interrogate either system or application data. Standard programming languages such as COBOL may be used, and generalized audit software is also available from the accounting firms such as System 2190 from KPMG. Specific retrieval software such as EasyTree from SRA can also be obtained. Increasingly, there is a large range of third-party software products available for the development of CATs. Some of the most widely known include IDEA, Interactive Data Extraction and Analysis, ACL, Auditor Command Language, SQL, Structured Query Language used with relational databases, SAS, Statistical Analysis Software. There is also a wide variety of other third-party software which can assist in an audit review, such as CA Examine for a review of the IBM MVS operating system or the Enterprise Security Manager from Accent for a review of Unix. Embedded data collection. This is similar to the interrogation software, but the program logic is embedded within the live application program or systems software. Parallel simulation. This involves the rewriting of a system and processing data through it so that the results can be compared to the live system. Others. There are a variety of other tools such as code comparison software which can compare two files containing either data or program code and highlight differences. Administration tools. A large range of products is now available to assist in the effective running of the internal audit function. These can be developed in-house or acquired from third-party suppliers. In some instances, such as planning software, generally available products such as PMW can be used, although audit-specific products are increasingly becoming available. Not only do such products simplify the administration of the function, but they also provide a more professional service for the organization. Typically, products will be used for such areas as planning, risk assessment, time recording, electronic working papers, and presentations. Authentication. We have seen that encryption offers a way of constraining the set of possible receivers of a message. Constraining the set of potential senders of a message is called authentication. Authentication is thus complementary to encryption. Authentication is also useful for proving that a message has not been modified. In this section, we discuss authentication as a constraint on possible senders of a message. Note that this sort of authentication is similar to but distinct from user authentication. An authentication algorithm using symmetric keys consists of the following components: a set K of keys, a set M of messages, a set A of authenticators. A function S, K tends to M tends to A, that is, for each K epsilon K, Sk is a function for generating authenticators from messages. Both S and Sk for any K should be efficiently computable functions. A function V, K tends to M cross A tends to true, false, that is, for each K epsilon K, Vk is a function for verifying authenticators on messages. Both V and Vk for any K should be efficiently computable functions. The critical property that an authentication algorithm must possess is this. For a message M, a computer can generate an authenticator A epsilon A such that Vk of M A equals true only if it possesses K. Thus, a computer holding K can generate authenticators on messages so that any computer possessing K can verify them. However, a computer not holding K cannot generate authenticators on messages that can be verified using Vk. Since authenticators are generally exposed, for example, sent on a network with the messages themselves, it must not be feasible to derive K from the authenticators. Practically, if Vk of Ma equals true, then we know that M has not been modified and that the sender of the message has K. If we share K with only one entity, then we know that the message originated from K. Just as there are two types of encryption algorithms, there are two main varieties of authentication algorithms. The first step in understanding these algorithms is to explore hash functions. A hash function, HM function, creates a small fixed-sized block of data known as a message digest or hash value from a message M. Hash function work by taking a message, splitting it into blocks and processing the blocks to produce an n-bit hash. H must be collision resistant, that is, it must be infeasible to find an M inverted comma not equal to M such that HM function equals to HM inverted comma function. Now, if HM function equals to HM inverted comma function, we know that M equals to M inverted comma, that is, we know that the message has not been modified. Common message digest functions include MD5, now considered insecure, which provides a 128-bit hash, and SHA1, which outputs a 160-bit hash. Message digests are useful for detecting changed messages but unuseful as authenticators. For example, HM function can be sent along with the message, but if H is known, then someone could modify M to M inverted commas and recompute HM inverted commas function, and the message modification would not be detected. Therefore, we must authenticate HM function. The first main type of authentication algorithm uses symmetric encryption. In a message authentication code, MAC, a cryptographic checksum is generated from the message using a secret key. A MAC provides a way to securely authenticate short values. If we use it to authenticate HM function for an H that is collision resistant, then we obtain a way to securely authenticate long messages by hashing them first. Note that K is needed to compute both SK and VK, so anyone able to compute one can compute the other. The second main type of authentication algorithm is a digital signature algorithm, and the authenticators thus produced are called digital signatures. Digital signatures are very useful in that they enable anyone to verify the authenticity of the message. In a digital signature algorithm, it is computationally infeasible to derive KS from KV. Thus, KV is the public key and KS is the private key. Note that encryption and authentication may be used together or separately. Sometimes, for instance, we want authentication but not confidentiality. For example, a company could provide a software patch and could sign that patch to prove that it came from the company and that it hasn't been modified. Authentication is a component of many aspects of security. For example, digital signatures are the core of non-repudiation, which supplies proof that an entity performed an action. A typical example of non-repudiation involves the filing out of electronic forms as an alternative to the signing of paper contracts. Non-repudiation assures that a person filing out an electronic form cannot deny that he did so. Key distribution. Certainly, a good part of the battle between cryptographers, those inventing ciphers, and cryptanalysts, those trying to break them, involves keys. With symmetric algorithms, both parties need the key and no one else should have it. The delivery of the symmetric key is a huge challenge. Sometimes it is performed out of band, say via a paper document or a conversation. These methods do not scale well, however. Also consider the key management challenge. Suppose a user wanted to communicate with n other users privately. That user would need n keys and, for more security, would need to change those keys frequently. These are the very reasons for efforts to create asymmetric key algorithms. Not only can the keys be exchanged in public, but a given user needs only one private key no matter how many other people she wants to communicate with. There is still the matter of managing a public key for each recipient of the communication, but since public keys need not be secured, simple storage can for that key ring. Unfortunately, even the distribution of public keys requires some care. Consider the man in the middle attack shown in figure below. Here the person who wants to receive an encrypted message sends out his public key, but an attacker also sends her bad public key which matches her private key. The person who wants to send the encrypted message knows no better and so uses the bad key to encrypt the message. The attacker then happily decrypts it. The problem is one of authentication. What we need is proof of who or what owns a public key. One way to solve that problem involves the use of digital certificates. A digital certificate is a public key digitally signed by a trusted party. The trusted party receives proof of identification from some entity and certifies that the public key belongs to that entity. But how do we know we can trust the certifier? These certificate authorities have their public keys included within web browsers and other consumers of certificates before they are distributed. The certificate authorities can then vouch for other authorities, digitally signing the public keys of these other authorities and so on, creating a web of trust. The certificates can be distributed in a standard X.509 digital certificate format that can be passed by a computer. Common criteria. Common criteria evaluations are performed on computer security products and systems. Common criteria (CC) is a set of internationally and nationally recognized technical standards and configurations that allow for security evaluations of information technology (IT) products and technology. The individual set of common criteria technical standards or configurations developed for a specific product or technology is qualified as a protection profile. Common criteria is a framework in which computer system users can specify their security functional and assurance requirements, SFRs and SARs respectively. Through the use of protection profiles, vendors can then implement and/or make claims about the security attributes of their products, and testing laboratories can evaluate the products to determine if they actually meet the claims. In other words, common criteria provides assurance that the process of specification, implementation and evaluation of a computer security product has been conducted in a rigorous and standard and repeatable manner at a level that is commensurate with the target environment for use. Key concepts. Target of evaluation, TOE. The product or system that is the subject of the evaluation. The evaluation serves to validate claims made about the target. To be of practical use, the evaluation must verify the target's security features. This is done through the following. Protection Profile (PP). A document typically created by a user or user community which identifies security requirements for a class of security devices, for example, smart cards used to provide digital signatures or network firewalls relevant to the user for a particular purpose. Product vendors can choose to implement products that comply with one or more PPs and have their products evaluated against those PPs. In such a case, a PP may serve as a template for the product's ST security target as defined below, or the authors of the ST will at least ensure that all requirements in relevant PPs also appear in the target's ST document. Customers looking for particular types of products can focus on those certified against the PP that meets their requirements. Security Target ST. The document that identifies the security properties of the target of evaluation. It may refer to one or more PPs. The TOE is evaluated against the SFRs, see below, established in its ST, no more and no less. This allows vendors to tailor the evaluation to accurately match the intended capabilities of their product. This means that a network firewall does not have to meet the same functional requirements as a database management system, and that different firewalls may in fact be evaluated against completely different lists of requirements. The ST is usually published so that potential customers may determine the specific security features that have been certified by the evaluation. Security Functional Requirements, SFRs. Specify individual security functions which may be provided by a product. The common criteria presents a standard catalog of such functions. For example, a SFR may state how a user acting a particular role might be authenticated. The list of SFRs can vary from one evaluation to the next, even if two targets are the same type of product. Although common criteria does not prescribe any SFRs to be included in an ST, it identifies dependencies where the correct operation of one function, such as the ability to limit access according to roles, is dependent on another, such as the ability to identify individual roles. The evaluation process also tries to establish the level of confidence that may be placed in the product's security features through quality assurance processes. Security Assurance Requirements (SARs). Descriptions of the measures taken during development and evaluation of the product to assure compliance with the claimed security functionality. For example, an evaluation may require that all source code is kept in a change management system or that full functional testing is performed. The common criteria provides a catalog of these, and the requirements may vary from one evaluation to the next. The requirements for particular targets or types of products are documented in the ST and PP respectively. Evaluation Assurance Level (EAL). The numerical rating describing the depth and rigor of an evaluation. Each EAL corresponds to a package of security assurance requirements, SARs, see above, which covers the complete development of a product with a given level of strictness. Common criteria lists 7 levels, with EAL 1 being the most basic and therefore cheapest to implement and evaluate, and EAL 7 being the most stringent and most expensive. Normally, an ST or PP author will not select assurance requirements individually, but choose one of these packages, possibly augmenting requirements in a few areas with requirements from a higher level. Higher EALs do not necessarily imply better security. They only mean that the claimed security assurance of the TOE has been more extensively verified. Computer Security Classifications. The U.S. Department of Defense Trusted Computer System Evaluation Criteria specify 4 security classifications in systems A, B, C, and D. This specification is widely used to determine the security of a facility and to model security solutions, so we explore it here. The lowest level classification is Division D or Minimal Protection. Division D includes only one class and is used for systems that have failed to meet the requirements of any of the other security classes. For instance, MS-DOS and Windows 3.1 are in Division D. Division C, the next level of security, provides discretionary protection and accountability of users and their actions through the use of audit capabilities. Division C has 2 levels, C1 and C2. A C1 class system incorporates some form of controls that allow users to protect private information and to keep other users from accidentally reading or destroying their data. A C1 environment is one in which cooperating users access data at the same levels of sensitivity. Most versions of Unix are C1 class. The total of all protection systems within a computer system, hardware, software, firmware, that correctly enforce a security policy is known as a Trusted Computer Base, TCB. The TCB of a C1 system controls access between users and files by allowing the user to specify and control sharing of objects by named individuals or defined groups. In addition, the TCB requires that the users identify themselves before they start any activities that the TCB is expected to mediate. This identification is accomplished via a protected mechanism or password. The TCB protects the authentication data so that they are inaccessible to unauthorized users. A C2 class system adds an individual-level access control to the requirements of a C1 system. For example, access rights of a file can be specified to the level of a single individual. In addition, the system administrator can selectively audit the actions of any one or more users based on individual identity. The TCB also protects itself from modification of its code or data structures. In addition, no information produced by a prior user is available to another user who accesses a storage object that has been released back to the system. Some special, secure versions of Unix have been certified at the C2 level. Division B mandatory protection systems have all the properties of a Class 2 system. In addition, they attach a sensitivity label to each object in the system. The B1 class TCB maintains these labels, which are used for decisions pertaining to mandatory access control. For example, a user at the confidential level could not access a file at the more sensitive secret level. The TCB also denotes the sensitivity level at the top and bottom of each page of any human-readable output. In addition to the normal user name password authentication information, the TCB also maintains the clearance and authorizations of individual users and will support at least 2 levels of security. These levels are hierarchical so that a user may access any objects that carry sensitivity labels equal to or lower than his security clearance. For example, a secret level user could access a file at the confidential level in the absence of other access controls. Processes are also isolated through the use of distinct address spaces. A B2 class system extends the sensitivity labels to each system resource, such as storage objects. Physical devices are assigned minimum and maximum security levels that the system uses to enforce constraints imposed by the physical environments in which the devices are located. In addition, a B2 system supports covert channels and the auditing of events that could lead to the exploitation of a covert channel. A B3 class system allows the creation of access control lists that denote users or groups not granted access to a given named object. The TCB also contains a mechanism to monitor events that may indicate a violation of security policy. The mechanism notifies the security administrator and, if necessary, terminates the event in the least disruptive manner. The highest level classification is Division A. Architecturally, a Class A1 system is functionally equivalent to a B3 system, but it uses formal design specifications and verification techniques, granting a high degree of assurance that the TCB has been implemented correctly. A system beyond Class A1 might be designed and developed in a trusted facility by trusted personnel. The use of a TCB merely ensures that the system can enforce aspects of a security policy. The TCB does not specify what the policy should be. Encryption. As it solves a wide variety of communication security problems, encryption is used frequently in many aspects of modern computing. It is used to send messages securely across a network as well as to protect database, data, files, and even entire disks from having their contents read by unauthorized entities. An encryption algorithm enables the sender of a message to ensure that only a computer possessing a certain key can read the message, or ensure that the writer of data is the only reader of that data. Encryption of messages is an ancient practice, of course, and there have been many encryption algorithms dating back to ancient times. In this section, we describe important modern encryption principles and algorithms. An encryption algorithm consists of the following components: a set K of keys, a set M of messages, a set C of cipher texts. An encrypting function E:(K leads to M leads to C function, that is, for each K epsilon K, EK is a function for generating cipher texts from messages. Both E and EK for any K should be efficiently computable functions. Generally, EK is a randomized mapping from messages to cipher texts. A decrypting function D:(K leads to C leads to M function, that is, for each K epsilon K, DK is a function for generating messages from ciphertexts. Both D and DK for any K should be efficiently computable functions. An encryption algorithm must provide this essential property. Given a ciphertext C epsilon C, a computer can compute M such that EK M equals to C only if it possesses K. Thus, a computer holding K can decrypt ciphertexts to the plain text used to produce them, but a computer not holding K cannot decrypt ciphertexts. Since ciphertexts are generally exposed, for example sent on a network, it is important that it be infeasible to derive K from the ciphertexts. There are two main types of encryption algorithms: symmetric and asymmetric. We discuss both types in the following sections. Symmetric encryption. In a symmetric encryption algorithm, the same key is used to encrypt and to decrypt. Therefore, the secrecy of K must be protected. Figure below shows an example of two users communicating securely via symmetric encryption over an insecure channel. Note that the key exchange can take place directly between the two parties or via a trusted third party, that is, a certificate authority. For the past several decades, the most commonly used symmetric encryption algorithm in the United States for civilian applications has been the Data Encryption Standard (DES) cipher adopted by the National Institute of Standards and Technology (NIST). DES works by taking a 64-bit value and a 56-bit key and performing a series of transformations that are based on substitution and permutation operations. Because DES works on a block of bits at a time, is known as a block cipher, and its transformations are typical of block ciphers. With block ciphers, if the same key is used for encrypting an extended amount of data, it becomes vulnerable to attack. DES is now considered insecure for many applications because its keys can be exhaustively searched with moderate computing resources. Note, though, that it is still frequently used. Rather than giving up on DES, NIST created a modification called triple DES, in which the DES algorithm is repeated 3 times, 2 encryptions and 1 decryption on the same plain text using 2 or 3 keys. For example, C equals to EK3 into DK2 into EK1 M function. When 3 keys are used, the effective key length is 168 bits. Triple DES is in widespread use today. In 2001, NIST adopted a new block cipher called the Advanced Encryption Standard (AES) to replace DES. AES is another block cipher. It can use key lengths of 128, 192 or 256 bits and works on a 128-bit blocks. Generally, the algorithm is compact and efficient. Block ciphers are not in themselves secure encryption schemes. In particular, they do not directly handle messages longer than their required block sizes. However, there are many modes of encryption that are based on stream ciphers which can be used to securely encrypt longer messages. RC4 is perhaps the most common stream cipher. A stream cipher is designed to encrypt and decrypt a stream of bytes or bits rather than a block. This is useful when the length of a communication would make a block cipher too slow. The key is input into a pseudo-random bit generator, which is an algorithm that attempts to produce random bits. The output of the generator when fed a key is a key stream. A key stream is an infinite set of bits that can be used to encrypt a plain text stream by simply XORing it with the plain text. XOR, for exclusive OR, is an operation that compares 2 input bits and generates 1 output bit. If the bits are the same, the result is 0. If the bits are different, the result is 1. RC4 is used in encrypting streams of data, such as in WEP, the wireless LAN protocol. Unfortunately, RC4, as used in WEP, IEEE standard 802.11, has been found to be breakable in a reasonable amount of computer time. In fact, RC4 itself has vulnerabilities. Asymmetric encryption. In an asymmetric encryption algorithm, there are different encryption and decryption keys. An entity preparing to receive encrypted communication creates 2 keys and makes one of them called the public key available to anyone who wants it. Any sender can use that key to encrypt a communication, but only the key creator can decrypt the communication. The scheme known as public key encryption was a breakthrough in cryptography. No longer must a key be kept secret and delivered securely. Instead, anyone can encrypt a message to the receiving entity, and no matter who else is listening, only that entity can decrypt the message. As an example of how public key encryption works, we describe an algorithm known as RSA after its inventors Rivest, Shamir, and Adelman. RSA is the most widely used asymmetric encryption algorithm. Asymmetric algorithms based on elliptic curves are gaining ground, however, because the key length of such an algorithm can be shorter for the same amount of cryptographic strength. In RSA, KE is the public key and KD is the private key. N is the product of two large randomly chosen prime numbers P and Q. For example, P and Q are 512 bits each. It must be computationally infeasible to derive KD, N from KE, N so that KE need not be kept secret and can be widely disseminated. The encryption algorithm is EKE, N of M equals MKE mod N, where KE satisfies KE KD mod of P minus 1 into Q minus 1 equals 1. The decryption algorithm is then DKD, N of C equals to CKD mod N. An example using small values is shown in figure. In this example, we make P equals 7 and Q equals 13. We then calculate N equals to 7 into 13 equaling 91 and P minus 1 of Q minus 1 equals to 72. We next select KE relatively prime to 72 and less than 72, yielding 5. Finally, we calculate KD such that KE KD mod 72 equals 1, yielding 29. We now have our keys. The public key KE N equals 5, 91, and private key KD N equals 29, 91. Encrypting the message 69 with the public key results in the message 62, which is then decoded by the receiver via the private key. The use of asymmetric encryption begins with the publication of the public key of the destination. For bidirectional communication, the source also must publish its public key. Publication can be as simple as handing over an electronic copy of the key, or it can be more complex. The private key or secret key must be zealously guarded, as anyone holding that key can decrypt any message created by the matching public key. We should note that the seemingly small difference in key use between asymmetric and symmetric cryptography is quite large in practice. Asymmetric cryptography is much more computationally expensive to execute. It is much faster for a computer to encode and decode ciphertext by using the usual symmetric algorithms than by using asymmetric algorithms. Why then use an asymmetric algorithm? In truth, these algorithms are not used for general-purpose encryption of large amounts of data. However, they are used not only for encryption of small amounts of data, but also for authentication, confidentiality, and key distribution, as we show in the following sections. One-time passwords. To avoid the problems of password sniffing and shoulder surfing, a system can use a set of paired passwords. When a session begins, the system randomly selects and presents one part of a password pair. The user must supply the other part. In this system, the user is challenged and must respond with the correct answer to that challenge. This approach can be generalized to the use of an algorithm as a password. Such algorithmic passwords are not susceptible to reuse. That is, a user can type in a password and no entity intercepting that password will be able to reuse it. In this scheme, the system and the user share a symmetric password. The password PW is never transmitted over a medium that allows exposure. Rather, the password is used as input to the function along with a challenge CH presented by the system. The user then computes the function H PWCH function. The result of this function is transmitted as the authenticator to the computer. Because the computer also knows PW and CH, it can perform the same computation. If the results match, the user is authenticated. The next time the user needs to be authenticated, another CH is generated and the same steps ensue. This time, the authenticator is different. This one-time password system is one of only a few ways to prevent improper authentication due to password exposure. One-time password systems are implemented in various ways. Commercial implementations use hardware calculators with a display or a display and numeric keypad. These calculators generally take the shape of a credit card, a keychain dongle, or a USB device. Software running on computers or smartphones provide the user with PWCH function. PW can be input by the user or generated by the calculator in synchronization with the computer. Sometimes PW is just a personal identification number, PIN. The output of any of these systems shows the one-time password. A one-time password generator that requires input by the user involves two-factor authentication. Two different types of components are needed in this case. For example, a one-time password generator that generates the correct response only if the PIN is valid. Two-factor authentication offers far better authentication protection than single-factor authentication because it requires something you have as well as something you know. Another variation on one-time passwords uses a code book or one-time pad, which is a list of single-use passwords. Each password on the list is used once and then is crossed out or erased. The commonly used S-key system uses either software, calculator, or a code book based on these calculations as a source of one-time passwords. Policy management. Policy management is a technology that can simplify the complex task of managing networks and distributed systems. Under this paradigm, an administrator can manage different aspects of a network or distributed system in a flexible and simplified manner by deploying a set of policies that govern its behavior. Policies are technology-independent rules aiming to enhance the hard-coded functionality of managed devices by introducing interpreted logic that can be dynamically changed without modifying the underlying implementation. This allows for a certain degree of programmability without the need to interrupt the operation of either the managed system or of the management system itself. Policy conflict. As with any programmable system, a policy-driven one can suffer from inconsistencies incurred by contradicting rules governing its behavior. These are known as policy conflicts and come about as a result of specification errors, omissions, or contradictory management operations and, in some cases, can have catastrophic effects on the operation of the managed system. They have also been described as being analogous to software bugs that occur when two or more policies are activated simultaneously, enforcing contradictory management operations on the system. Classification of policy conflicts. Policy conflicts are broadly classified into domain-independent and application-specific, where the former, as the names suggest, are independent of the policy application and the latter are bound by the constraints of the application domain. Example application domains that have been considered in the literature include quality of service (QoS) in IP networks, distributed systems, firewall security, and call control in telecommunication networks. Policy conflicts can also be classified according to the time frame at which they can be detected. Static conflicts can be detected through offline analysis at policy specification time, whereas dynamic conflicts can only be detected when policies are enforced, as they depend on the current state of the managed system. For example, conflicts can occur between policies for dynamically allocating resources and those setting quotas for users or classes of service. As such, automation should be a key aspect of dynamic analysis mechanisms so that the operational impact of a conflict can be kept to a minimum. Detection and resolution of policy conflicts. To effectively use policies and drive the functionality of a managed system in a consistent manner, it is necessary to check that newly created policies do not conflict with each other or with policies already deployed in the system. To achieve this, detection processes utilize information regarding the conditions under which conflicts can arise to search policy spaces and identify policies that meet the conflict criteria. Based on the types of conflicts identified in the literature and the different application domains in which they occur, research has concentrated in the development of mechanisms and techniques for their effective detection. Although simple conflicts, example modality conflicts, can be detected by syntactic analysis, more specialized inconsistencies require a precise definition of the conditions for a conflict, which sometimes include domain-specific knowledge and processes that utilize such information to signal the occurrence of a conflict. Popular approaches for the detection of conflicts have been based on meta-policies, detection rules, policy relationships, applicability spaces, and information models. Resolution in the latter part of policy analysis, which aims at handling detected inconsistencies, preferably in an automated manner so that consistency among policies can be restored. The process of resolving conflicts may involve retracting, suppressing, prioritizing, or amending policies, and in some cases enforcing a new policy altogether so that consistency among policy rules can be restored. The methodology in doing so depends heavily on the type of policies involved and the domain in which conflicts occur. Although human intervention is unavoidable in some situations, several research efforts focused on techniques to automate the resolution process where possible. Popular approaches for the resolution of conflicts have been based on meta-policies, resolution rules, precedents, policy ordering, and conflict prevention. The time frame at which conflicts can be detected influences the analysis methodology and requirements for dealing with them. Static conflicts are typically detected through analysis initiated manually by the system administrator. Conflicts represent inconsistencies between policies and are typically resolved by amending the policies. In contrast, runtime conflicts must be detected by a process that monitors policy enforcement and detects inconsistent situations in the system's execution. Resolution must be achieved automatically, for example through enforcing resolution rules. Lack of automation in the handling of runtime conflicts may have catastrophic consequences on the correct system operation, especially when managing QoS for delay-sensitive applications. Policy refinement. Ideally, a policy-based management system should facilitate the definition of high-level administrative goals, which are easy for humans to express and understand, enable their translation into low-level policies, and map them into commands that configure the managed devices accordingly. While the high-level goals reflect the business objectives of the network administrator, the low-level policies are responsible for device-level configurations. Policy refinement is the process of transforming a high-level goal or abstract policy specification into low-level, concrete policies that can be enforced on the managed system. The main tasks of the refinement process are the following. Determine the resources that are needed to satisfy the requirements of the policy. Translate high-level goals into operational policies that the system can enforce. Verify the low-level policies actually meet the requirements specified by the high-level goal. Several policy refinement approaches have been developed. Program threats. Processes along with the kernel are the only means of accomplishing work on a computer. Therefore, writing a program that creates a breach of security or causing a normal process to change its behavior and create a breach is a common goal of crackers. In fact, even most non-program security events have as their goal causing a program threat. For example, while it is useful to log into a system without authorization, it is quite a lot more useful to leave behind a backdoor daemon that provides information or allows easy access even if the original exploit is blocked. Trojan horse. A text editor program, for example, may include code to search the file to be edited for certain keywords. If any are found, the entire file may be copied to a special area accessible to the creator of the text editor. A code segment that misuses its environment is called a Trojan horse. Long search paths, such as are common on Unix systems, exacerbate the Trojan horse problem. The search path lists the set of directories to search when an ambiguous program name is given. The path is searched for a file of that name and the file is executed. All the directories in such a search path must be secure, or a Trojan horse could be slipped into the user's path and executed accidentally. For instance, consider the use of the dot character in a search path. The dot tells the shell to include the current directory in the search. Thus, if a user has dot in her search path, has set her current directory to a friend's directory and enters the name of a normal system command, the command may be executed from the friend's directory. The program will run within the user's domain, allowing the program to do anything that the user is allowed to do, including deleting the user's file, for instance. A variation of the Trojan horse is a program that emulates a login program. An unsuspecting user starts to log in at a terminal and notices that he has apparently mistyped his password. He tries again and is successful. What has happened is that his authentication key and password have been stolen by the login emulator, which was left running on the terminal by the thief. The emulator stored away the password, printed out a login error message, and exited. The user was then provided with a genuine login prompt. This type of attack can be defeated by having the operating system print a usage message at the end of an interactive session, or by a non-trappable key sequence such as the Ctrl-Alt-Delete combination used by all modern Windows operating systems. Another variation on the Trojan horse is spyware. Spyware sometimes accompanies a program that the user has chosen to install. Most frequently, it comes along with freeware or shareware programs, but sometimes it is included with commercial software. The goal of spyware is to download ads to display on the user's system, create pop-up browser windows when certain sites are visited, or capture information from the user system and return it to a central site. This latter practice is an example of a general category of attacks known as covert channels in which surreptitious communication occurs. For example, the installation of an innocuous-seeming program on a Windows system could result in the loading of a spyware daemon. The spyware could contact a central site, be given a message and a list of recipient addresses, and deliver a spam message to those users from the Windows machine. This process continues until the user discovers the spyware. Frequently, the spyware is not discovered. In 2010, it was estimated that 90% of spam was being delivered by this method. This theft of service is not even considered a crime in most countries. Spyware is a micro-example of a macro problem, violation of the principle of least privilege. Under most circumstances, a user of an operating system does not need to install network daemons. Such daemons are installed via two mistakes. First, a user may run with more privileges than necessary, for example, as the administrator, allowing programs that she runs to have more access to the system than is necessary. This is a case of human error, a common security weakness. Second, an operating system may allow by default more privileges than a normal user needs. This is a case of poor operating system design decisions. An operating system, and indeed software in general, should allow fine-grained control of access and security, but it must also be easy to manage and understand. Inconvenient or inadequate security measures are bound to be circumvented, causing an overall weakening of the security they were designed to implement. Trapdoor. The designer of a program or system might leave a hole in the software that only she is capable of using. This type of security breach or trapdoor was shown in the movie War Games. For instance, the code might check for a specific user ID or password, and it might circumvent normal security procedures. Programmers have been arrested for embezzling from banks by including rounding errors in their code and having the occasional half-cent credited to their accounts. This account crediting can add up to a large amount of money, considering the number of transactions that a large bank executes. A clever trapdoor could be included in a compiler. The compiler could generate standard object code as well as a trapdoor, regardless of the source code being compiled. This activity is particularly nefarious since a search of the source code of the program will not reveal any problems. Only the source code of the compiler would contain the information. Trapdoors pose a difficult problem because, to detect them, we have to analyze all the source code for all components of a system. Given that software systems may consist of millions of lines of code, this analysis is not done frequently, and frequently it is not done at all. Logic bomb. Consider a program that initiates a security incident only under certain circumstances. It would be hard to detect because under normal operations there would be no security hole. However, when a predefined set of parameters was met, the security hole would be created. This scenario is known as a logic bomb. A programmer, for example, might write code to detect whether he was still employed. If that check failed, a daemon could be spawned to allow remote access, or code could be launched to cause damage to the site. Stack and buffer overflow. The stack or buffer overflow attack is the most common way for an attacker outside the system on a network or dial-up connection to gain unauthorized access to the target system. An authorized user of the system may also use this exploit for privilege escalation. Essentially, the attack exploits a bug in a program. The bug can be a simple case of poor programming in which the programmer neglected to code bounds checking on an input field. In this case, the attacker sends more data than the program was expecting. By usual trial and error or by examining the source code of the attacked program if it is available, the attacker determines the vulnerability and writes a program to do the following: overflow an input field, command line argument, or input buffer, for example, on a network daemon until it writes into the stack. Overwrite the current return address on the stack with the address of the exploit code loaded in step 3. Write a simple set of code for the next space in the stack that includes the commands that the attacker wishes to execute, for instance, spawn a shell. The result of this attack program's execution will be a root shell or other privileged command execution. For instance, if a web page form expects a username to be entered into a field, the attacker could send the username plus extra characters to overflow the buffer and reach the stack, plus a new return address to load onto the stack, plus the code the attacker wants to run. When the buffer reading subroutine returns from execution, the return address is the exploit code and the code is run. Let's look at a buffer overflow exploit in more detail. Consider the simple C program shown in figure below. C program with buffer overflow condition. This program creates a character array of buffer size and copies the contents of the parameter provided on the command line argument 1. As long as the size of this parameter is less than buffer size, we need 1 byte to store the null terminator. This program works properly. But consider what happens if the parameter provided on the command line is longer than buffer size. In this scenario, the strcopy function will begin copying from argument 1 until it encounters a null terminator or until the program crashes. Thus, this program suffers from a potential buffer overflow problem in which copied data overflow the buffer array. Note that a careful programmer could have performed bounds checking on the size of argument 1 by using the strncopy function rather than the strcopy function, replacing the line strcopy of buffer argument 1 with strncopy of buffer argument 1 size of buffer -1. Unfortunately, good bounds checking is the exception rather than the norm. Furthermore, lack of bounds checking is not the only possible cause of the behavior of the program in figure above. The program could instead have been carefully designed to compromise the integrity of the system. We now consider the possible security vulnerabilities of a buffer overflow. The program could instead have been carefully designed to compromise the integrity of the system. We now consider the possible security vulnerabilities of a buffer overflow. When a function is invoked in a typical computer architecture, the variables defined locally to the function, sometimes known as automatic variables, the parameters passed to the function and the address to which control returns once the function exits are stored in a stack frame. The layout for a typical stack frame is shown in figure below. Examining the stack frame from top to bottom, we first see the parameters passed to the function, followed by any automatic variables declared in the function. We next see the frame pointer, which is the address of the beginning of the stack frame. Finally, we have the return address, which specifies where to return control once the function exits. The frame pointer must be saved on the stack, as the value of the stack pointer can vary during the function call. The saved frame pointer allows relative access to parameters and automatic variables. Given this standard memory layout, a cracker could execute a buffer overflow attack. Her goal is to replace the return address in the stack frame so that it now points to the code segment containing the attacking program. The programmer first writes a shortcode segment such as the following. Using the execvp function system call, this code segment creates a shell process. If the program being attacked runs with system-wide permissions, this newly created shell will gain complete access to the system. Of course, the code segment could do anything allowed by the privileges of the attacked process. This code segment is then compiled so that the assembly language instructions can be modified. The primary modification is to remove unnecessary features in the codes, thereby reducing the code size so that it can fit into a stack frame. The assembled code fragment is now a binary sequence that will be at the heart of the attack. Refer again to the program shown for C program with buffer overflow condition. Let's assume that when the main function is called in that program, the stack frame appears as shown in figure below. Hypothetical stack frame for program A before and B after. Using a debugger, the programmer then finds the address of buffer 0 in the stack. That address is the location of the code the attacker wants executed. The binary sequence is appended with the necessary amount of no-op instructions for no operation to fill the stack frame up to the location of the return address and the location of buffer 0. The new return address is added. The attack is complete when the attacker gives this constructed binary sequence as input to the process. The process then copies the binary sequence from argv1 to position buffer 0 in the stack frame. Now, when control returns from the main function, instead of returning to the location specified by the old value of the return address, we return to the modified shell code which runs with the access rights of the attacked process. Figure above in B contains the modified shell code. There are many ways to exploit potential buffer overflow problems. In this example, we consider the possibility that the program being attacked, the code shown in figure for program of C program with buffer overflow condition, ran with system-wide permissions. However, the code segment that runs once the value of the return address has been modified might perform any type of malicious act such as deleting files, opening network ports for further exploitation, and so on. This example buffer overflow attack reveals that considerable knowledge and programming skill are needed to recognize exploitable code and then to exploit it. Unfortunately, it does not take great programmers to launch security attacks. Rather, one cracker can determine the bug and then write an exploit. Anyone with rudimentary computer skills and access to the exploit, a so-called script kiddie, can then try to launch the attack at target systems. The buffer overflow attack is especially pernicious because it can be run between systems and can travel over allowed communication channels. Such attacks can occur within protocols that are expected to be used to communicate with the target machine, and they can therefore be hard to detect and prevent. They can even bypass the security added by firewalls. One solution to this problem is for the CPU to have a feature that disallows execution of code in a stack section of memory. Viruses. Another form of program threat is a virus. A virus is a fragment of code embedded in a legitimate program. Viruses are self-replicating and are designed to infect other programs. They can wreak havoc in a system by modifying or destroying files and causing system crashes and program malfunctions. As with most penetration attacks, viruses are very specific to architectures, operating systems, and applications. Viruses are a particular problem for users of PCs. Unix and other multi-user operating systems generally are not susceptible to viruses because the executable programs are protected from writing by the operating system. Even if a virus does infect such a program, its powers usually are limited because other aspects of the system are protected. Viruses are usually born via email, with spam the most common vector. They can also spread when users download viral programs from internet file sharing services or exchange infected disks. Another common form of virus transmission uses Microsoft Office files, such as Microsoft Word documents. These documents can contain macros or Visual Basic programs that programs in the Office suite, Word, PowerPoint, and Excel will execute automatically because these programs run under the user's own account. The macros can run largely unconstrained, for example, deleting user files at will. Commonly, the virus will also email itself to others in the user's contact list. Here is a code sample that shows how simple it is to write a Visual Basic macro that a virus could use to format the hard drive of a Windows computer as soon as the file containing the macros was opened, as shown in figure. How do viruses work? Once a virus reaches a target machine, a program known as a virus dropper inserts the virus into the system. The virus dropper is usually a Trojan horse, executed for other reasons but installing the virus as its core activity. Once installed, the virus may do any one of a number of things. There are literally thousands of viruses, but they fall into several main categories. Note that many viruses belong to more than one category. File. A standard file virus infects a system by appending itself to a file. It changes the start of the program so that execution jumps to its code. After it executes, it returns control to the program so that its execution is not noticed. File viruses are sometimes known as parasitic viruses as they leave no full files behind and leave the host program still functional. Boot. A boot virus infects the boot sector of the system, executing every time the system is booted and before the operating system is loaded. It watches for other bootable media and infects them. These viruses are also known as memory viruses because they do not appear in the file system. Figure below shows how a boot virus works. Macro. Most viruses are written in a low-level language such as assembly or C. Macroviruses are written in a high-level language such as Visual Basic. These viruses are triggered when a program capable of executing the macro is run. For example, a macro virus could be contained in a spreadsheet file. Source code. A source code virus looks for source code and modifies it to include the virus and to help spread the virus. Polymorphic. A polymorphic virus changes each time it is installed to avoid detection by antivirus software. The changes do not affect the virus's functionality, but rather change the virus's signature. A virus signature is a pattern that can be used to identify a virus, typically a series of bytes that make up the virus code. Encrypted. An encrypted virus includes decryption code along with the encrypted virus, again to avoid detection. The virus first decrypts and then executes. Stealth. This tricky virus attempts to avoid detection by modifying parts of the system that could be used to detect it. For example, it could modify the read system call so that if the file it has modified is read, the original form of the code is returned rather than the infected code. Tunneling. This virus attempts to bypass detection by an antivirus scanner by installing itself in the interrupt handler chain. Similar viruses install themselves in device drivers. Multipartite. A virus of this type is able to infect multiple parts of a system, including boot sectors, memory, and files. This makes it difficult to detect and contain. Armored. An armored virus is coded to make it hard for antivirus researchers to unravel and understand. It can also be compressed to avoid detection and disinfection. In addition, virus droppers and other full files that are part of a virus infestation are frequently hidden via file attributes or unviewable file names. This vast variety of viruses has continued to grow. For example, in 2004, a new and widespread virus was detected. It exploited 3 separate bugs for its operation. This virus started by infecting hundreds of Windows servers, including many trusted sites running Microsoft Internet Information Server (IIS). Any vulnerable Microsoft Explorer web browser visiting those sites received a browser virus with any download. The browser virus installed several backdoor programs, including a keystroke logger, which records everything entered on the keyboard, including passwords and credit card numbers. It also installed a daemon to allow unlimited remote access by an intruder and another that allowed an intruder to route spam through the infected desktop computer. Generally, viruses are the most disruptive security attacks, and because they are effective, they will continue to be written and to spread. An active security-related debate within the computing community concerns the existence of a monoculture in which many systems run the same hardware, operating system, and application software. This monoculture supposedly consists of Microsoft products. One question is whether such a monoculture even exists today. Another question is whether, if it does, it increases the threat of and damage caused by viruses and other security intrusions. Protection. The processes in an operating system must be protected from one another's activities. To provide such protection, we can use various mechanisms to ensure that only processes that have gained proper authorization from the operating system can operate on the files, memory segments, CPU, and other resources of a system. Protection refers to a mechanism for controlling the access of programs, processes, or users to the resources defined by a computer system. This mechanism must provide a means for specifying the controls to be imposed, together with a means of enforcement. Goals of protection. We need to provide protection for several reasons. The most obvious is the need to prevent the mischievous, intentional violation of an access restriction by a user. Of more general importance, however, is the need to ensure that each program component active in a system uses system resources only in ways consistent with stated policies. This requirement is an absolute one for a reliable system. Protection can improve reliability by detecting latent errors at the interfaces between component subsystems. Early detection of interface errors can often prevent contamination of a healthy subsystem by a malfunctioning subsystem. Also, an unprotected resource cannot defend against use or misuse by an unauthorized or incompetent user. A protection-oriented system provides means to distinguish between authorized and unauthorized usage. The role of protection in a computer system is to provide a mechanism for the enforcement of the policies governing resource use. These policies can be established in a variety of ways. Some are fixed in the design of the system, while others are formulated by the management of a system. Still others are defined by the individual users to protect their own files and programs. A protection system must have the flexibility to enforce a variety of policies. Policies for resource use may vary by application and they may change over time. For these reasons, protection is no longer the concern solely of the designer of an operating system. The application programmer needs to use protection mechanisms as well to guard resources created and supported by an application subsystem against misuse. Mechanisms determine how something will be done. Policies decide what will be done. The separation of policy and mechanism is important for flexibility. Policies are likely to change from place to place or time to time. In the worst case, every change in policy would require a change in the underlying mechanism. Using general mechanisms enables us to avoid such a situation. Principles of protection. A key time-tested guiding principle for protection is the principle of least privilege. It dictates that programs, users, and even systems be given just enough privileges to perform their tasks. Consider the analogy of a security guard with a passkey. If this key allows the guard into just the public areas that she guards, then misuse of the key will result in minimal damage. If, however, the passkey allows access to all areas, then damage from its being lost, stolen, misused, copied, or otherwise compromised will be much greater. An operating system following the principle of least privilege implements its features, programs, system calls, and data structures so that failure or compromise of a component does the minimum damage and allows the minimum damage to be done. The overflow of a buffer in a system daemon might cause the daemon process to fail, for example, but should not allow the execution of code from the daemon process's stack that would enable a remote user to gain maximum privileges and access to the entire system, as happens too often today. Such an operating system also provides system calls and services that allow applications to be written with fine-grained access controls. It provides mechanisms to enable privileges when they are needed and to disable them when they are not needed. Also beneficial is the creation of audit trails for all privileged function access. The audit trail allows the programmer, system administrator, or law enforcement officer to trace all protection and security activities on the system. Managing users with the principle of least privilege entails creating a separate account for each user with just the privileges that the user needs. An operator who needs to mount tapes and backup files on the system has access to just those commands and files needed to accomplish the job. Some systems implement role-based access control (RBAC) to provide this functionality. Computers implemented in a computing facility under the principle of least privilege can be limited to running specific services, accessing specific remote hosts via specific services, and doing so during specific times. Typically, these restrictions are implemented through enabling or disabling each service and through using access control lists. The principle of least privilege can help produce a more secure computing environment. Unfortunately, it frequently does not. For example, Windows 2000 has a complex protection scheme at its core and yet has many security holes. Domain of protection. A computer system is a collection of processes and objects. By objects, we mean both hardware objects such as the CPU, memory segments, printers, disks and tape drives, and software objects such as files, programs and semaphores. Each object has a unique name that differentiates it from all other objects in the system, and each can be accessed only through well-defined and meaningful operations. Objects are essentially abstract data types. The operations that are possible may depend on the object. For example, on a CPU, we can only execute. Memory segments can be read and written, whereas a CD-ROM or DVD-ROM can only be read. Tape drives can be read, written, and rewound. Data files can be created, opened, read, written, closed, and deleted. Program files can be read, written, executed, and deleted. A process should be allowed to access only those resources for which it has authorization. Furthermore, at any time, a process should be able to access only those resources that it currently requires to complete its task. This second requirement, commonly referred to as the need-to-know principle, is useful in limiting the amount of damage a faulty process can cause in the system. For example, when process P invokes procedure A function, the procedure should be allowed to access only its own variables and the formal parameters passed to it. It should not be able to access all the variables of process P. Similarly, consider the case in which process P invokes a compiler to compile a particular file. The compiler should not be able to access files arbitrarily, but should have access only to a well-defined subset of files, such as the source file, listing file, and so on, related to the file to be compiled. Conversely, the compiler may have private files used for counting or optimization purposes that process P should not be able to access. The need-to-know principle is similar to the principle of least privilege, that the goals of protection are to minimize the risks of possible security violations. Domain structure. To facilitate the scheme just described, a process operates within a protection domain which specifies the resources that the process may access. Each domain defines a set of objects and the types of operations that may be invoked on each object. The ability to execute an operation on an object is an access right. A domain is a collection of access rights, each of which is an ordered pair, object name, rights set. For example, if domain D has the access right file F read-write function, then a process executing in domain D can both read and write file F. It cannot, however, perform any other operation on that object. Domains may share access rights. For example, in figure shows system with 3 protection domains. We have 3 domains, D1, D2, and D3. The access right, 4, print function is shared by D2 and D3, implying that a process executing in either of these 2 domains can print object 4. Note that a process must be executing in domain D1 to read and write object 1, while only processes in domain D3 may execute object 1. The association between a process and a domain may be either static if the set of resources available to the process is fixed throughout the process's lifetime, or dynamic. As might be expected, establishing dynamic protection domains is more complicated than establishing static protection domains. If the association between processes and domains is fixed and we want to adhere to the need-to-know principle, then a mechanism must be available to change the content of a domain. The reason stems from the fact that a process may execute in two different phases and may, for example, need read access in one phase and write access in another. If a domain is static, we must define the domain to include both read and write access. However, this arrangement provides more writes than are needed in each of the two phases, since we have read access in the phase where we need only write access and vice versa. Thus, the need-to-know principle is violated. We must allow the contents of a domain to be modified so that the domain always reflects the minimum necessary access rights. If the association is dynamic, a mechanism is available to allow domain switching, enabling the process to switch from one domain to another. We may also want to allow the content of a domain to be changed. If we cannot change the content of a domain, we can provide the same effect by creating a new domain with the changed content and switching to that new domain when we want to change the domain content. A domain can be realized in a variety of ways. Each user may be a domain. In this case, the set of objects that can be accessed depends on the identity of the user. Domain switching occurs when the user is changed, generally when one user logs out and another user logs in. Each process may be a domain. In this case, the set of objects that can be accessed depends on the identity of the process. Domain switching occurs when one process sends a message to another process and then waits for a response. Each procedure may be a domain. In this case, the set of objects that can be accessed corresponds to the local variables defined within the procedure. Domain switching occurs when a procedure call is made. Consider the standard dual mode, monitor user mode model of operating system execution. When a process executes in monitor mode, it can execute privileged instructions and thus gain complete control of the computer system. In contrast, when a process executes in user mode, it can invoke only non-privileged instructions. Consequently, it can execute only within its predefined memory space. These two modes protect the operating system executing in monitor domain from the user processes executing in user domain. In a multi-programmed operating system, two protection domains are insufficient since users also want to be protected from one another. Therefore, a more elaborate scheme is needed. Protocol security. A typical security system consists of a number of principles such as people, companies, computers, and magnetic card readers which communicate using a variety of channels including phones, email, radio, infrared, and by carrying data on physical devices such as bank cards and transport tickets. The security protocols are the rules that govern these communications. They are typically designed so that the system will survive malicious acts such as people telling lies on the phone, hostile governments jamming radio, or forgers altering the data on train tickets. Protection against all possible attacks is often too expensive, so protocols are typically designed under certain assumptions about the threats. Evaluating a protocol thus involves answering two questions. First, is the threat model realistic? Second, does the protocol deal with it? Protocols may be extremely simple, such as swiping a badge through a reader in order to enter a building, or they may be very complex. The world's networks of dozens of protocols specifying how a cash machine interacts with customers, how it talks to the bank that operates it, how the bank communicates with the network operator, how money gets settled between banks, how encryption keys are set up between the various principals, and what sort of alarm messages may be transmitted, such as instructions to capture a card. All these protocols have to work together in a large and complex system. Often, a seemingly innocuous design feature opens up a serious flaw. For example, in the past, a number of banks encrypted the customer's PIN using a key known only to their central computers and cash machines and wrote it to the card magnetic strip. The idea was to let the cash machine verify PINs locally, which saved on communications and even allowed a limited service to be provided when the cash machine was offline. After this system had been used for many years without incident, a programmer who was playing around with a card reader used in a building access control system discovered that he could alter the magnetic strip of his own bank card by substituting his wife's bank account number for his own. He could then take money out of her account using the modified card and his own PIN. He realized that this also enabled him to loot any other customer's account, and he went on to steal hundreds of thousands over a period of years. The affected banks had to spend millions on changing their systems, so we need to look systematically at security protocols and how they fail. As they are widely deployed and often very badly designed, I'll give a number of examples from different applications. Password eavesdropping risks, the MIG in the middle attack, reflection attacks, manipulating the message, and so on. Password eavesdropping risks. Passwords are still the foundation on which much of computer security rests, as they are the main mechanism used to authenticate human users to computer systems. In the form of pins, they are also used in many embedded systems, from cash machines through mobile phones to burglar alarms. They raise many problems, such as the difficulty people have in choosing passwords that are difficult to guess or remembering passwords generated randomly by the system. For now, let us consider the limitations of embedded systems that use passwords. The typical application is the remote control used to open your garage or to unlock the doors of cars manufactured up to the mid-1990s. These primitive remote controls just broadcast their 16-bit serial number, which also acts as the password. An attack that became common was to use a grabber, a device that would record a code and replay it later. These devices, seemingly from Taiwan, arrived on the market in about 1995. They enabled thieves lurking in parking lots to record the signal used to lock a car door and then replay it to unlock the car once the owner had left. One countermeasure was to use separate codes for lock and unlock. But this is still not ideal. First, the thief could lurk outside your house and record the unlock code before you drive away in the morning. He can then come back at night and help himself. Second, 16-bit passwords are too short. In the mid-1990s, devices appeared that could try all possible codes one after the other. A code would be found on average after about 215 tries, which at 10 per second would take less than an hour. A thief operating in a parking lot with 100 vehicles within range could be rewarded in less than a minute with a car helpfully flashing its lights. Another countermeasure was to double the length of the password from 16 to 32 bits. The manufacturers proudly advertised over 4 billion codes, but this only showed they hadn't really understood the problem. There was still only one code or two codes for each car, and although guessing was now impractical, grabbers still worked fine. The MIG in the middle attack. There is an interesting attack on challenge response systems that appears to have played a role in bringing peace to southern Africa. The ever-increasing speeds of warplanes in the 1930s and 1940s, together with the invention of the jet engine, radar, and rocketry, made it ever more difficult for air defense forces to tell their own craft apart from the enemy's. This led to a serious risk of fratricide, people shooting down their colleagues by mistake, and drove the development of identity friend or foe (IFF) systems. These were first fielded in World War II and in their early form enabled an airplane illuminated by radar to broadcast an identifying number to signal friendly intent. In 1952, this system was adopted to identify civil aircraft to air traffic controllers, and worried about the loss of security once it became widely used, the U.S. Air Force started a research program to incorporate cryptographic protection in the system. Nowadays, the typical air defense system sends random challenges with its radar signals, and friendly aircraft have equipment and keys that enable them to identify themselves with correct responses. US aircraft use an IFF system called Mode 12, and systems are under development for ground troops too. But the South African Air Force SAAF had been cut off from Western arms supplies by sanctions and had to design its own system. In the late 1980s, South African troops were fighting a war in northern Namibia and southern Angola. The goals were to keep Namibia under white rule and to impose a client government, UNITA, on Angola. Because the South African Defence Force consisted largely of conscripts from a small white population, it was essential to limit casualties. So most South African troops remained in Namibia on policing duties while the fighting to the north was done by UNITA troops. The role of the SAAF was twofold: to provide tactical support to UNITA by bombing targets in Angola and to ensure that the Angolans and their Cuban allies did not return the compliment in Namibia. Suddenly, Cuban aircraft broke through the South African air defenses and bombed a South African camp in northern Namibia, killing a number of white conscripts. This proof that its air supremacy had been lost helped the Pretoria government decide to hand over Namibia to the insurgents, itself a huge step on the road to a majority rule in South Africa several years later. The raid may have been the last successful military operation ever carried out by Soviet bloc forces. Some years afterward, a former SAAF officer told me how the Cubans had pulled it off. Several MiGs had loitered in southern Angola, just north of the South African air defense belt, until a flight of SAAF Impala bombers raided a target in Angola. Then the MiGs turned sharply and flew openly through the SAAF's air defenses, which sent IFF challenges. The MiGs relayed them to the Angolan air defense batteries, which transmitted them at a SAAF bomber. The responses were relayed back in real time to the MiGs, which retransmitted them and were allowed through. See figure below. According to my informant, this had a significant effect on the general staff in Pretoria. Being not only outfought by black opponents, but actually outsmarted was not consistent with the worldview they had held until then. We have no independent confirmation on this story from the Angolan or Cuban side. But the basic technique is at least as old as World War II and illustrates the basic idea behind an attack known to the cryptographic community as the man-in-the-middle or, more recently, the middle-person attack. We will come across it again and again in applications ranging from pay TV to internet security protocols. It even applies in online gaming. As the mathematician John Conway once remarked, it's easy to beat a grandmaster at postal chess. Just play two grandmasters at once, one as white and the other as black, and relay the moves between them. In many cases, middle-person attacks are possible but not economic. In the case of car keys, it should certainly be possible to steal a car by having an accomplice follow the driver and electronically relay the radio challenge to you as you work the lock, but it would be a lot simpler to just pick the driver's pocket or mug him. Revocation of access rights. In a dynamic protection system, we may sometimes need to revoke access rights to objects shared by different users. Various questions about revocation may arise. Immediate versus delayed. Does revocation occur immediately or is it delayed? If revocation is delayed, can we find out when it will take place? Selective versus general. When an access right to an object is revoked, does it affect all the users who have an access right to the object, or can we specify a select group of users whose access rights should be revoked? Partial versus total. Can a subset of the rights associated with an object be revoked, or must we revoke all access rights for this object? Temporary versus permanent. Can access be revoked permanently, that is, the revoked access right will never again be available, or can access be revoked and later be obtained again? With an access list scheme, revocation is easy. The access list is searched for any access rights to be revoked and they are deleted from the list. Revocation is immediate and can be general or selective, total or partial, and permanent or temporary. Capabilities, however, present a much more difficult revocation problem as mentioned earlier. Since the capabilities are distributed throughout the system, we must find them before we can revoke them. Schemes that implement revocation for capabilities include the following. Reacquisition. Periodically, capabilities are deleted from each domain. If a process wants to use a capability, it may find that the capability has been deleted. The process may then try to reacquire the capability. If access has been revoked, the process will not be able to reacquire the capability. Back pointers. A list of pointers is maintained with each object, pointing to all capabilities associated with that object. When revocation is required, we can follow these pointers, changing the capabilities as necessary. This scheme was adopted in the Multics system. It is quite general, but its implementation is costly. Indirection. The capabilities point indirectly, not directly, to the objects. Each capability points to a unique entry in a global table which in turn points to the object. We implement revocation by searching the global table for the desired entry and deleting it. Then, when an access is attempted, the capability is found to point to an illegal table entry. Table entries can be reused for other capabilities without difficulty, since both the capability and the table entry contain the unique name of the object. The object for a capability and its table entry must match. The scheme was adopted in the CAL system. It does not allow selective revocation. Keys. A key is a unique bit pattern that can be associated with a capability. This key is defined when the capability is created, and it can be neither modified nor inspected by the process that owns the capability. A master key is associated with each object. It can be defined or replaced with the set key operation. When a capability is created, the current value of the master key is associated with the capability. When the capability is exercised, its key is compared with the master key. If the keys match, the operation is allowed to continue. Otherwise, an exception condition is raised. Revocation replaces the master key with a new value via the set key operation, invalidating all previous capabilities for this object. The scheme does not allow selective revocation since only one master key is associated with each object. If we associate a list of keys with each object, then selective revocation can be implemented. Finally, we can group all keys into one global table of keys. A capability is valid only if its key matches some key in the global table. We implement revocation by removing the matching key from the table. With this scheme, a key can be associated with several objects and several keys can be associated with each object, providing maximum flexibility. In key-based schemes, the operations of defining keys, inserting them into lists, and deleting them from lists should not be available to all users. In particular, it would be reasonable to allow only the owner of an object to set the keys for that object. This choice, however, is a policy decision that the protection system can implement but should not define. Security. Security, on the other hand, requires not only an adequate protection system but also consideration of the external environment within which the system operates. A protection system is ineffective if user authentication is compromised or a program is run by an unauthorized user. Computer resources must be guarded against unauthorized access, malicious destruction or alteration, and accidental introduction of inconsistency. These resources include information stored in the system, both data and code, as well as the CPU, memory, disks, tapes, and networking that are the computer. The security problem. In many applications, ensuring the security of the computer system is worth considerable effort. Large commercial systems containing payroll or other financial data are inviting targets to thieves. Systems that contain data pertaining to corporate operations may be of interest to unscrupulous competitors. Furthermore, loss of such data, whether by accident or fraud, can seriously impair the ability of the corporation to function. We discussed mechanisms that the operating system can provide with appropriate aid from the hardware that allow users to protect their resources, including programs and data. These mechanisms work well only as long as the users conform to the intended use of and access to these resources. We say that a system is secure if its resources are used and accessed as intended under all circumstances. Unfortunately, total security cannot be achieved. Nonetheless, we must have mechanisms to make security breaches a rare occurrence rather than the norm. Security violations or misuse of the system can be categorized as intentional, malicious, or accidental. It is easier to protect against accidental misuse than against malicious misuse. For the most part, protection mechanisms are the core of protection from accidents. The following list includes several forms of accidental and malicious security violations. We should note that in our discussion of security, we use the terms intruder and cracker for those attempting to breach security. In addition, a threat is the potential for a security violation, such as the discovery of a vulnerability, whereas an attack is the attempt to break security. Breach of confidentiality. This type of violation involves unauthorized reading of data or theft of information. Typically, a breach of confidentiality is the goal of an intruder. Capturing secret data from a system or a data stream, such as credit card information or identity information for identity theft, can result directly in money for the intruder. Breach of integrity. This violation involves unauthorized modification of data. Such attacks can, for example, result in passing of liability to an innocent party or modification of the source code of an important commercial application. Breach of availability. This violation involves unauthorized destruction of data. Some crackers would rather wreak havoc and gain status or bragging rights than gain financially. Website defacement is a common example of this type of security breach. Theft of service. This violation involves unauthorized use of resources. For example, an intruder or intrusion program may install a daemon on a system that acts as a file server. Denial of service. This violation involves preventing legitimate use of the system. Denial of service (DOS) attacks are sometimes accidental. The original internet worm turned into a DOS attack when a bug failed to delay its rapid spread. Attackers use several standard methods in their attempts to breach security. The most common is masquerading, in which one participant in a communication pretends to be someone else, another host, or another person. By masquerading, attackers breach authentication, the correctness of identification. They can then gain access that they would not normally be allowed or escalate their privileges, obtain privileges to which they would not normally be entitled. Another common attack is to replay a captured exchange of data. A replay attack consists of the malicious or fraudulent repeat of a valid data transmission. Sometimes the replay comprises the entire attack, for example, in a repeat of a request to transfer money. But frequently it is done along with message modification, again to escalate privileges. Consider the damage that could be done if a request for authentication had a legitimate user's information replaced with an unauthorized user's. Yet another kind of attack is the man-in-the-middle attack, in which an attacker sits in the data flow of a communication, masquerading as the sender to the receiver and vice versa. In a network communication, a man-in-the-middle attack may be preceded by a session hijacking in which an active communication session is intercepted. Several attack methods are depicted in figure. Figure shows standard security attacks. As we have already suggested, absolute protection of the system from malicious abuse is not possible, but the cost to the perpetrator can be made sufficiently high to deter most intruders. In some cases, such as a denial of service attack, it is preferable to prevent the attack but sufficient to detect the attack so that countermeasures can be taken. To protect a system, we must take security measures at 4 levels. Physical. The site or sites containing the computer systems must be physically secured against armed or surreptitious entry by intruders. Both the machine rooms and the terminals or workstations that have access to the machines must be secured. Human. Authorization must be done carefully to ensure that only appropriate users have access to the system. Even authorized users, however, may be encouraged to let others use the access in exchange for a bribe, for example. They may also be tricked into allowing access via social engineering. One type of social engineering attack is phishing. Here, a legitimate-looking email or web page misleads a user into entering confidential information. Another technique is dumpster diving, a general term for attempting to gather information in order to gain unauthorized access to the computer by looking through trash, finding phone books, or finding notes containing passwords, for example. These security problems are management and personal issues, not problems pertaining to operating systems. Operating system. The system must protect itself from accidental or purposeful security breaches. A runaway process could constitute an accidental denial of service attack. A query to a service could reveal passwords. A Stack Overflow could allow the launching of an unauthorized process. The list of possible breaches is almost endless. Network. Much computer data in modern systems travels over private leased lines, shared lines like the internet, wireless connections, or dial-up lines. Intercepting these data could be just as harmful as breaking into a computer, and interruption of communications could constitute a remote denial of service attack, diminishing users' use of and trust in the system. Security at the first 2 levels must be maintained if operating system security is to be ensured. A weakness at a high level of security, physical or human, allows circumvention of strict low-level operating system security measures. Thus, the old adage that a chain is only as strong as its weakest link is especially true of system security. All of these aspects must be addressed for security to be maintained. Furthermore, the system must provide protection to allow the implementation of security features. Without the ability to authorize users and processes to control their access and to log their activities, it would be impossible for an operating system to implement security measures or to run securely. Hardware protection features are needed to support an overall protection scheme. For example, the system without memory protection cannot be secure. New hardware features are allowing systems to be made more secure. Unfortunately, little in security is straightforward. As intruders exploit security vulnerabilities, security countermeasures are created and deployed. This causes intruders to become more sophisticated in their attacks. For example, recent security incidents include the use of spyware to provide a conduit for spam through innocent systems. This cat-and-mouse game is likely to continue, with more security tools needed to block the escalating intruder techniques and activities. Security within the operating system and between operating systems is implemented in several ways, ranging from passwords for authentication through guarding against viruses to detecting intrusions. System threats. Program threats typically use a breakdown in the protection mechanisms of a system to attack programs. In contrast, system and network threats involve the abuse of services and network connections. System and network threats create a situation in which operating system resources and user files are misused. Sometimes a system and network attack is used to launch a program attack and vice versa. The more open an operating system is, the more services it has enabled and the more functions it allows, the more likely it is that a bug is available to exploit. Increasingly, operating systems strive to be secure by default. For example, Solaris 10 moved from a model in which many services, FTP, Telnet and others, were enabled by default when the system was installed to a model in which almost all services are disabled at installation time and must specifically be enabled by system administrators. Such changes reduce the system's attack surface, the set of ways in which an attacker can try to break into the system. In the remainder of this section, we discuss some examples of system threats, including worms, port scanning, and denial of service attacks. It is important to note that masquerading and replay attacks are also commonly launched over networks between systems. In fact, these attacks are more effective and harder to counter when multiple systems are involved. For example, within a computer, the operating system usually can determine the sender and receiver of a message. Even if the sender changes to ID of someone else, there may be a record of that ID change. When multiple systems are involved, especially systems controlled by attackers, then such tracing is much more difficult. In general, we can say that sharing secrets to prove identity and as keys to encryption is required for authentication of encryption, and sharing secrets is easier in environments such as a single operating system in which secure sharing methods exist. These methods include shared memory and inter-process communications. Worms. A worm is a process that uses the spawn mechanism to duplicate itself. The worm spawns copies of itself, using up system resources and perhaps locking out all other processes. On computer networks, worms are particularly potent since they may reproduce themselves among systems and thus shut down an entire network. Such an event occurred in 1988 to Unix systems on the Internet, causing the loss of system and system administrator time worth millions of dollars. At the close of the workday on November 2, 1988, Robert Tappan Morris Jr., a first-year Cornell graduate student, unleashed a worm program on one or more hosts connected to the Internet. Targeting Sun Microsystems Sun 3 workstations and VAX computers running variants of version 4 BSD Unix, the worm quickly spread over great distances. Within a few hours of its release, it had consumed system resources to the point of bringing down the infected machines. Although Morris designed the self-replicating program for rapid reproduction and distribution, some of the features of the Unix networking environment provided the means to propagate the worm throughout the system. It is likely that Morris chose for initial infection an Internet host left open for and accessible to outside users. From there, the worm program exploited flaws in the Unix operating system's security routines and took advantage of a Unix utilities that simplify resource sharing in local area networks to gain unauthorized access to thousands of other connected sites. Morris's methods of attack are outlined next. The worm was made up of two programs, a grappling hook, also called a bootstrap or vector program, and the main program. Named I.C, the grappling hook consisted of 99 lines of C code compiled and run on each machine it accessed. Once established on the computer system under attack, the grappling hook connected to the machine where it originated and uploaded a copy of the main worm onto the hooked system, shown in figure below. The main program proceeded to search for other machines to which the newly infected system could connect easily. In these actions, Morris exploited the Unix networking utility Remote Shell for easy remote task execution. By setting up special files that list host login name pairs, users can omit entering a password each time they access a remote account on the paired list. The worm searched these special files for site names that would allow remote execution without a password. Where remote shells were established, the worm program was uploaded and began executing anew. The attack via remote access was one of the 3 infection methods built into the worm. The other 2 methods involved operating system bugs in the Unix Finger and SendMail programs. The Finger utility functions as an electronic telephone directory. The command Finger user name at hostname returns a person's real and login names along with other information that the user may have provided, such as office and home address and telephone numbers, research plan, or clever quotation. Finger runs as a background process or daemon at each BSD site and responds to queries throughout the Internet. The worm executed a buffer overflow attack on Finger. The program queried Finger with a 536-byte string crafted to exceed the buffer allocated for input and to overwrite the stack frame. Instead of returning to the main routine where it resided before Morris's call, the Finger daemon was routed to a procedure within the invading 536-byte string now residing on the stack. The new procedure executed /bin/sh, which, if successful, gave the worm a remote shell on the machine under attack. The bug exploited in SendMail also involved using a daemon process for malicious entry. SendMail sends, receives, and routes electronic mail. Debugging code in the utility permits testers to verify and display the state of the mail system. The debugging option was useful to system administrators and was often left on. Morris included in his attack arsenal a call to debug that, instead of specifying a user address, as would be normal in testing, issued a set of commands that mailed and executed a copy of the grappling hook program. Once in place, the main worm systematically attempted to discover user passwords. It began by trying simple cases of no password or passwords constructed of account username combinations, then used comparisons with an internal dictionary of 432 favorite password choices, and then went to the final stage of trying each word in the standard Unix online dictionary as a possible password. This elaborate and efficient 3-stage password cracking algorithm enabled the worm to gain access to other user accounts on the infected system. The worm then searched for remote shell data files in these newly broken accounts and used them as described previously to gain access to user accounts on remote systems. With each new access, the worm program searched for already active copies of itself. If it found one, the new copy exited, except in every 7th instance. Had the worm exited on all duplicate sightings, it might have remained undetected. Allowing every 7th duplicate to proceed, possibly to confound efforts to stop its spread by baiting with fake worms, created a wholesale infestation of Sun and VAX systems on the Internet. The very features of the Unix network environment that assisted in the worm's propagation also helped to stop its advance. Ease of electronic communication, mechanisms to copy source and binary files to remote machines, and access to both source code and human expertise allowed cooperative efforts to develop solutions quickly. By evening of the next day, November 3rd, methods of halting the invading program were circulated to system administrators via the Internet. Within days, specific software patches for the exploited security flaws were available. Port scanning. Port scanning is not an attack but rather a means for a cracker to detect a system's vulnerabilities to attack. Port scanning typically is automated, involving a tool that attempts to create a TCP/IP connection to a specific port or a range of ports. For example, suppose there is a known vulnerability or bug in SendMail. A cracker could launch a port scanner to try to connect, say, to port 25 of a particular system or to a range of systems. If the connection was successful, the cracker or tool could attempt to communicate with the answering service to determine if the service was indeed SendMail and, if so, if it was the version with the bug. Now imagine a tool in which each bug of every service of every operating system was encoded. The tool could attempt to connect to every port of one or more systems. For every service that answered, it could try to use each known bug. Frequently, the bugs are buffer overflows, allowing the creation of a privileged command shell on the system. From there, of course, the cracker could install Trojan horses, backdoor programs, and so on. There is no such tool, but there are tools that perform subsets of that functionality. For example, Nmap from http://www.insecure.org/nmap/ is a very versatile open source utility for network exploration and security auditing. When pointed at a target, it will determine what services are running, including application names and versions. It can identify the host operating system. It can also provide information about defenses, such as what firewalls are defending the target. It does not exploit any known bugs because port scans are detectable. They frequently are launched from zombie systems. Such systems are previously compromised, independent systems that are serving their owners while being used for various purposes, including denial of service attacks and spam relay. Zombies make crackers particularly difficult to prosecute because determining the source of the attack and the person that launched it is challenging. This is one of many reasons for securing inconsequential systems, not just systems containing valuable information or services. Denial of service. As mentioned earlier, denial of service attacks are aimed not at gaining information or stealing resources, but rather at disrupting legitimate use of a system or facility. Most such attacks involve systems that the attacker has not penetrated. Launching an attack that prevents legitimate use is frequently easier than breaking into a machine or facility. Denial of service attacks are generally network-based. They fall into two categories. Attacks in the first category use so many facility resources that, in essence, no useful work can be done. For example, a website click could download a Java applet that proceeds to use all available CPU time or to pop up windows infinitely. The second category involves disrupting the network of the facility. There have been several successful denial-of-service attacks of this kind against major websites. These attacks result from abuse of some of the fundamental functionality of TCP/IP. For instance, if the attacker sends the part of the protocol that says, "I want to start a TCP connection," but never follows with the standard, "The connection is now complete," the result can be partially started TCP session. If enough of these sessions are launched, they can eat up all the network resources of the system, disabling any further legitimate TCP connections. Such attacks, which can last hours or days, have caused partial or full failure of attempts to use the target facility. The attacks are usually stopped at the network level until the operating systems can be updated to reduce their vulnerability. Generally, it is impossible to prevent denial-of-service attacks. The attacks use the same mechanisms as normal operation. Even more difficult to prevent and resolve are distributed denial-of-service (DDoS) attacks. These attacks are launched from multiple sites at once toward a common target, typically by zombies. DDoS attacks have become more common and are sometimes associated with blackmail attempts. A site comes under attack and the attackers offer to halt the attack in exchange for money. Sometimes the site does not even know it is under attack. It can be difficult to determine whether a system slowdown is an attack or just a surge in system use. Consider that a successful advertising campaign that greatly increases traffic to a site could be considered a DDoS. There are other interesting aspects of DOS attacks. For example, if an authentication algorithm locks an account for a period of time after several incorrect attempts to access the account, then an attacker could cause all authentication to be blocked by purposely making incorrect attempts to access all accounts. Similarly, a firewall that automatically blocks certain kinds of traffic could be induced to block that traffic when it should not. These examples suggest that programmers and system managers need to fully understand the algorithms and technologies they are deploying. Finally, computer science classes are notorious sources of accidental system DOS attacks. Consider the first programming exercises in which students learn to create subprocessor threads. A common bug involves spawning subprocessors infinitely. Threat monitoring. Check for suspicious patterns of activity, that is, several incorrect password attempts may signal password guessing. Audit log records the time, user and type of all accesses to an object, useful for recovery from a violation and developing better security measures. Scan the system periodically for security holes, done when the computer is relatively unused. Check for short or easy to guess passwords, unauthorized set UID programs, unauthorized programs in system directories, unexpected long-running processes, improper directory protections, improper protections on system data files, dangerous entries in the program search path, Trojan horse, changes to system programs, monitor checksum values. User Account Controls, UAC. User Account Control (UAC) is a feature in Windows that can help you stay in control of your computer by informing you when a program makes a change that requires administrator-level permission. UAC works by adjusting the permission level of your user account. If you're doing tasks that can be done as a standard user, such as reading email, listening to music, or creating documents, you have the permissions of a standard user, even if you're logged on as an administrator. When changes are going to be made to your computer that require administrator-level permission, UAC notifies you. If you are an administrator, you can click Yes to continue. If you are not an administrator, someone with an administrator account on the computer will have to enter their password for you to continue. If you give permission, you are temporarily given the rights of an administrator to complete the task, and then your permissions are returned back to that of a standard user. This makes it so that even if you're using an administrator account, changes cannot be made to your computer without you knowing about it, which can help prevent malicious software, malware, and spyware from being installed on or making changes to your computer. Tasks that require UAC attempts. Tasks that require administrative privileges will trigger a UAC prompt if UAC is enabled. They are typically marked by a security shield icon with the four colors of the Windows logo in Vista and Windows Server 2008, or with two panels, yellow and two blue, Windows 7, Windows Server 2008, R2 and later. In the case of executable files, the icon will have a security shield overlay. The following tasks require administrator privileges: running an application as an administrator, changes to system-wide settings or to files in system root or program files, installing and uninstalling applications, installing device drivers, installing ActiveX controls, changing settings for Windows Firewall, changing UAC settings, configuring Windows Update, adding or removing user accounts, changing a user's account type, configuring parental controls, running task scheduler, restoring backed up system files, viewing or changing another user's folders and files, running disk defragmenter, running registry editor, running the Windows Experience Index assessment. Virtual Private Networks (VPN). A virtual private network (VPN) provides a secure connection between a sender and a receiver over a public non-secure network such as the Internet. A secure connection is generally associated with private networks. A private network is a network that is owned or at least controlled via leased lines by an organization. Using the techniques discussed later in this chapter, a VPN can transform the characteristics of a public non-secure network into those of a private secure network. VPNs reduce remote access costs by using public network resources. Compared to other solutions including private networks, a VPN is inexpensive. VPNs are not new. In fact, they have been used in telephone networks for years and have become more prevalent since the development of the intelligent network. Frame relay networks, which have been around for some time, are VPNs. Virtual private networks are only new to IP networks such as the Internet. Therefore, some authors use the terms Internet VPN and Virtual Private Data Network to distinguish the VPN described from other VPNs. The goal of a VPN is to provide a secure passage for users' data over the non-secure Internet. It enables companies to use the Internet as the virtual backbone for their corporate networks by allowing them to create secure virtual links between their corporate office and branch or remote offices via the Internet. The cost benefits of VPN service have prompted corporations to move more of their data from private WANs to Internet-based VPNs. A VPN uses data encryption and other security mechanisms to prevent unauthorized users from accessing data and to ensure that data cannot be modified without detection as it flows through the Internet. It then uses the tunneling process to transport the encrypted data across the Internet. Tunneling is a mechanism for encapsulating one protocol in another protocol. In the context of the Internet, tunneling allows such protocols as IPX, AppleTalk, and IP to be encrypted and then encapsulated in IP. Similarly, in the context of VPNs, tunneling disguises the original network layer protocol by encrypting the packet and enclosing the encrypted packet in an IP envelope. This IP envelope, which is an IP packet, can then be transported securely across the Internet. At the receiving side, the envelope is removed and the data it contains is decrypted and delivered to the appropriate access device, such as a router. Simply put, a corporation is creating a private tunnel through the Internet for the secure delivery of its data. The tunnel enables the corporation to create a virtual WAN within the Internet that is cheaper than private WANs and safe from intruders. VPNs also provide quality of service (QoS) guarantees, which usually specify an upper bound on the average packet delay in the network. The guarantees may also include specification of a lower bound on the bandwidth available to the user. These guarantees are developed through service-level agreements (SLAs) with the service provider. Most service providers have their own private backbone IP networks. Therefore, they are in a better position to meet QoS guarantees. However, such networks do not provide the global coverage as the Internet. Sometimes a service provider makes private peering arrangements with other service providers whose private IP networks cover more area. This arrangement allows the service provider to hand off its high-priority traffic, that is, traffic with stringent QoS requirements, to networks with a guaranteed QoS instead of putting such high-priority traffic on the Internet where delay is unpredictable. From the preceding discussion, we can define a VPN by the following relationship. VPN equals tunneling plus security plus QoS guarantees. The remainder of the chapter deals with different tunneling techniques used to create VPNs. Advantages of VPNs. VPNs are inexpensive. They provide remote and mobile user with the access to the corporate network at the price of a local call. VPNs also provide the framework for corporate intranets and extranets. Corporations can exploit the global nature of the Internet and use VPNs to link all branch offices into private networks called intranets. A corporation can make certain sections of its intranet accessible to its vendors and strategic partners by means of the extranet. VPN tunnels permit non-routable protocols to be delivered to specific LAN segments in the corporate intranet. In this way, VPNs enable legacy applications to use the intranet. VPNs have also contributed significantly to the increased use of private IP addresses. Since applications are tunneled rather than routed across the WAN, companies can assign their own addresses as long as addresses are not advertised to the outside world. Types of VPNs. Currently, there are 3 types of VPNs. While their goal is to leverage the Internet as a private enterprise backbone network, each of them addresses the needs of a different interest group in the enterprise. The 3 types of VPNs are as follows. Access VPNs provide remote users such as road warriors or mobile users, telecommuters, and branch offices with reliable access to corporate networks. Intranet VPNs allow branch offices to be linked to corporate headquarters in a secure manner. Extranet VPNs allow customers, suppliers, and partners to access corporate intranet in a secure manner. VPN architectures. A VPN consists of our components, a VPN client, a network access server NAS, a tunnel terminating service or VPN server, and a VPN protocol. In a typical access VPN connection, a remote user or VPN client initiates a PPP connection with the ISP's NAS via the public switched telephone network PSTN. An NAS is a device that terminates dial-up calls over analog basic telephone service or digital ISDN circuits. The NAS is owned by the ISP and is usually implemented in the ISP's POP. After the user has been authenticated by the appropriate authentication method, the NAS directs the packet to the tunnel that connects both the NAS and the VPN server. The VPN server may reside in the ISP's POP or at the corporate site depending on the VPN model that is implemented. The VPN server recovers the packet from the tunnel, unwraps it, and delivers it to the corporate network. Figure below illustrates VPN architecture. There are 4 tunneling protocols used to establish VPNs, and 3 are extensions of the point-to-point protocol PPP. Point Tunneling Protocol PPTP, Layer 2 Forwarding L2F, Layer 2 Tunneling Protocol L2TP, IP Security IPsec Protocol Suite. When both PPTP and L2F were submitted to the IETF, the organization decided to combine the features of both protocols into a common tunneling protocol, which is now L2TP. The Layer 2 tunneling protocol was in the draft stage at the time of writing. The 4 protocols can be classified broadly into 2 groups, Layer 2 tunneling protocols and Layer 3 tunneling protocols. PPTP, L2F, and L2TP are Layer 2 tunneling protocols, while IPsec is a Layer 3 tunneling protocol. Conclusion. In this chapter, we have covered the following in detail. Protection, goals of protection, domain of protection, access matrix, implementation of access matrix, revocation of access rights, security, the security problem, authentication, one-time passwords, program threats, system threats, threat monitoring, encryption, computer security classifications, common criteria, VPN protocol security, access checks, ACL, DACLs, auditing and policy management, user account controls, UAC.